Welcome to Lecture 19 of our series on prosody. For prosody applications, and increasingly for research, machine learning is very important. In this lecture, we overview some options in the choices of features and of models. So, machine learning is generally used to create a model, often for some practical need. For example, to take as input some speech signal and decide if it is stressed or unstressed, or what tone it is, as discussed in the previous lecture. Or to identify the speaker, or to make some classification regarding his status, or his instantaneous mental state, or his intentions. Now, machine learning requires features as input, and these can be of various types. So this lecture is about the choices. In terms of the overview, back from lecture 14, anything may be used, including even meaningful features, if those are available, which usually require hand labeling, but if they're available, they can be useful. To simplify the discussion, we'll consider a continuum of feature types, specifically 4, which we'll cover from right to left, starting with meaningful features. So by meaningful features, these are things that have some significance in some language or in some theory, like H versus L tones, or the L star plus H, the late peak pattern of English, or the tag emphasis, which you may wish to specify to tell a speech synthesizer to treat some words specially. So these are designed, as you may guess, by linguists or by engineers wanting to give users control. The hope is that these are general. In reality, these usually turn out to be language dependent, theory internal, genre specific, maybe only really relevant to read speech, and worst of all, not automatically computable. So their utility is limited, but for linguistic investigations, they have a lot of value. The next option is to use mid-level features, things like the pitch height over a syllable. These are useful very generally. They encode fewer assumptions. They're a little bit closer related to general perceptions. One advantage that they have over frame-level features, our next topic, is that they can be fixed in length. So characterize the prosody of a 5-second sentence versus a 3-second sentence. If you're going by frame-level features, you will have more for the longer utterance. But mid-level features can be designed so that any utterance can be represented by the same number of features, which is advantageous for many machine learning models. The drawback is that if you've got many choices of which mid-level features to use and how to parameterize them, and they're not always robust. Very useful for different linguistic and psycholinguistic investigations. Another option is frame-level features, low-level things like intensity or reduction computed every 10 milliseconds throughout the signal. Many of these very carefully designed and validated, very clear for people, have written special purpose code and released it open source to compute these things as reliably as possible. They tend to be universal. They're based on extracting some information about the articulatory state of the speaker, regardless of the language or anything else. The big drawback is, since these are just individual measurements, making sense of them requires very powerful models to detect the average or the slope or tendencies or more complex temporal patterns, such as recursive neural networks. These are useful for phonetics research, speech synthesis, many other tasks. Now, modeling for prosody-related tasks does not always require prosody-specific features, so our final options are to use non-specific features that generically capture many aspects of the speech signal and are not specifically about just prosody. These features I'll talk about next also work well for non-prosodic tasks like phoneme recognition. 2 broad options. The first is the old option. 10 years ago or so, there was a lot of interest in making decisions, prosody-related decisions, based directly on the signal, or on a sort of trivial re-representation of the signal in terms of a filter bank, such as mel-frequency capsule coefficients, MFCCs. The drawback of using these super low-level features is that they require very, very powerful models. They can be used for various classification regression tasks. But over the past 2 or 3 years, a sort of better option, generally better option, has emerged, and that's the use of pre-trained models features. So the idea here is you pre-train a model on some pseudo task for example, to predict what happens next in speech. So you may have 500 hours of data, and you may chop it up in little pieces. You have some input, and then the output is to predict what's going to happen in the next half second. What exactly is the speech signal going to be in the next half second? It's a very challenging task, but if you can train a model with enough data, and you have, say, a 12-layer neural network with attention and conformers and whatnot in it, the performance can be surprisingly good. So many people have produced pre-trained speech models with things like names like Hubert and WaveTorVec2, and you can download these. In the process of solving these pseudo-tasks, these models re-represent the speech signal internally in features that are useful. And those features can then be used as input to some classification, whatever specific classification you're interested in, detecting sarcasm, detecting persuasiveness. So the advantage of this approach is, once you've got the model pre-trained, once you've got the parameters for computing those features, those internal features, training for the downstream model requires only modest data, maybe an hour of labeled sarcastic, non-sarcastic data. Because the features already contain so much information, the model can be relatively simpler. The drawbacks are you tend to end up with thousands of features, and the models tend to be completely uninterpretable. Still, if you're only interested in performance, this does seem to be the way to go for many tasks. All right, so that was all a little bit vague. If we think about some specific tasks, what feature set type might be best for each? It's complicated. New advances are constantly being made, but I can summarize with a table showing some tendencies I see in some of the best recent work for very specific needs. Check marks means effective, frequently used, and a dash means it's been tried and often found wanting. We'll talk more about some of these specific needs later. Okay, so to summarize, we have a continuum here. On the non-specific feature or simple feature side, you're making fewer assumptions. In some cases, you can get better performance and more robustness, depending upon what training data you have. Towards the mid-level or meaningful feature side, since the features have more complexity, more smarts built in, you need less training data to adapt it to whatever specific task you're trying to solve, which means the machine learning models can be simpler, trained with less data, and more explainable. So these can give insight. And the problem of controllability and transferability across genres, that's a big open question, no matter what feature set you're using. Okay, so that's it for our overview of feature choices for machine learning applications. And this wraps up our first set of technically focused lectures. In the next lecture, we'll go back to talking about the functions of prosody, starting with paralinguistics.